Hello, everybody, and welcome to another wonderful day of physical chemistry. So far this semester, we've been dealing with objects that more or less go back and forth in a straight box. But it turns out straight lines aren't the only possible motion that we can have. It also turns out things can move in, arcs. And one of the good ways to kind of look at this is, again, coming off of vibrations, if I have N2, so far all we've talked about is maybe the translation of the entire molecule and the vibrations back and forth. But it turns out those aren't the only types of motion available to a molecule. An important class is going to be the rotations themselves. So it's actually possible for a molecule to undergo rotational motion, and we can try and build this up in a similar way to the vibrational motion. We can go ahead and place one atom in the center and kind of watch what happens when an object of mass m just moves in a circular path in an xy plane, just circling around each other. Now, it is worth noting that true vibrations are going to have a lot more motion than this, but it's a pretty good first description of a diatomic molecule. We'll have to bring in some other features later, but for now, we're just going to talk about one atom rotating about the other atom. Now, if I've got this, we got a couple of things that we can, of descriptions we can use to help simplify our system. First of all, since we know from vibrations that the distance, the bond distance isn't going to change too much, we're going to treat R as being relatively fixed. If nothing else, we've come up with an independent description for that. And the potential is pretty much going to be identical for any place around the circle. So we're going to say that the potential energy for this rotation is zero, because any given point is as good as another, so they all have the same potential. Let's call it zero. So this is called a free rotor. And the free part is denoting this constant potential. So it's a free particle, just only does vibrations. This is also sometimes called a fixed rotor due to the fixed r distance. So as usual, I now have a movement of a particle. The first thing I'm going to do is I'm going to come up uh, with a Hamiltonian. So we're going to call this again the rigid rotor for that fixed r distance. And we now have essentially a particle moving in the xy plane. So I've got my two-dimensional Hamiltonian that I'm going to apply to my wave function. However, it turns out that this isn't going to be the most convenient way to describe this system, because I have a fixed distance. Well, there's no good way to express the fixed radii or fixed bond length in Cartesian coordinates. So I apologize. This is going to be the first of many times where we're going to flip to cylindrical coordinates. So we're going to be working a lot in cylindrical and spherical coordinates this semester. So it's possible to go ahead and turn xy into spherical coordinates. If you need a review, go ahead and do your calc lectures. I'm going to kind of take this based on faith. So we can turn our second derivative in xy to a second derivative with r and phi. So r is going to be our bond length, phi is going to be our location along the rotor. However, we already established this is going to be a rigid rotor. The important part about rigid rotor here is going to be actually the rigid part. So we're going to assume that our system has a fixed bond distance, at which point, anytime we have a derivative with respect to R just kind of drops out because, well, it ain't changing. So we can knock this term and this term, and all we're going to be left with is, again, our good old set of constants, Planck's and mass. And now we can determine the rotational moment for a predetermined bond length, which again is typically going to come from our harmonic oscillator or Morse potential. And then we're going to go ahead and see how our system changes with the choice of theta. So we can then apply this to a wave function, and we should be able to pop out our rotational energy in the wave function. So this means we need an eigenfunction and a eigenvector. All right. this is going to be a little bit tricky because we need to first take a step back and need a better way to describe the movement of our system. And for that, we're going to really need to build up an angular notation. So what we're going to be doing is trying to take a lot of what we had for Cartesian movement and turn this into a radial sort of basis. So the first thing we're going to need to do is actually replace our uh, replace our mass with something called moment of inertia. So a good way to look at a moment of inertia is it's going to be the resistance of the object to essentially any change in movement. So for simple one dimensions, that's just going to be the mass of our system. However, it gets a little bit messier when we're talking about angular motion because now I also have to resist this changing of direction. And it turns out the further out my particle is, the harder it is to change position. If you don't believe me, go ahead and take your textbook, hold it next to you, and go ahead and swirl in place. And then hold it out at arm's length and do the same thing. Guess which one's harder to do? And so that's really what we're essentially doing here. Now, to calculate a true moment of inertia, what we're going to need to do is calculate sum up the mass of the object times how far away it is from the center of movement squared. So this actually is a little bit messy for a real system because we almost always have more than one object. However, what we're often going to do is start with a simpler description of I only have one particle moving around a center. So in this case, that R is just going to be the bond length. However, it is worth noting that if I'm dealing with a diatomic molecule, we can replace this mass with reduced mass. However, there's a reason why the typical first system described is usually something like HCl or hydrogen iodide, where the particle out on the outside is very light and the particle in the center is very heavy, at which point pretty much the center ain't moving and all the movement comes from the hydrogen atom. So if you are having a diatomic system like that, either use the reduced mass or you're looking at the movement of the lighter atom around the heavier one. So using this moment of inertia, we can build up a momentum term. But instead of our good old friend linear momentum, we've got angular momentum. It's pretty much the same thing. So except for this time, what we're generating is our angular momentum is going to be based on the moment of inertia times the angular velocity, omega. Yes, I'm sorry, omega keeps getting used for everything. One of the things I want to make note, though, for this angular velocity is that it's actually going to be given in radians per second. Radians is unfortunately not exactly the easiest unit to use because remember, there's 2 pi radians in a circle, which means that the conversion in between angular velocity and something simpler like RPM, which is rotations per minute, or even RPS, or rotations per second, get a little bit awkward because of this radians rotations conversion. But it is simply going to be related by that issue of 2 pi. So something worth keeping in mind. However, one of the other things we have to deal with is that it turns out that like momentum, angular momentum does have a directional component. So I've got my particle moving in the y plane, but it turns out I'm going to have a different angular momentum if it's rotating clockwise versus counterclockwise. And so for this, we'd more or less just need a common convention. So if the particle is rotating clockwise, so this is going to be clockwise as given from below. This is going to give us a positive angular momentum. If it's moving counterclockwise, this is going to give us a negative angular momentum. So the classic description of this is usually given as the right-hand rule. So to illustrate this, what I want you to do is take your hand, put it out in front of you along the diagram. Point your thumb up and then see what direction your hand moves. The thumb is going to be the angular momentum. The way your hand moves when you curl it around is going to be the movement of the particle. So if the particle is moving clockwise, clockwise as seen from below, this is going to be counterclockwise as seen from above. The angular momentum is positive, and then the reverse for the negative direction. So again, it's this from below ends up being a very crucial feature. So take some time, play around with the right-hand rule. We'll try and practice it a bit in class. Now, in order to mathematically describe our angular momentum, we can use, not too surprisingly, an angular momentum operator. So the angular momentum operator for this z direction, so angular momentum going up, is given by a combination of position and momentum operators, which, as you may notice, is going to be hell on any sort of separability of our wave functions, which is something we're going to have to acknowledge a little bit later. But one of the things that we can notice is that it's essentially going to be combined by applying our x position operator on our y momentum and our y position operator on our x momentum. And essentially by pairing these together, you get angular momentum. So again, one of the ways to think about it, if I have a heavier moving object further away from center, so heavier object moving fast in the y direction, far away from the center, this is going to lead to a large angular momentum. And that's kind of what we're seeing here. However, as you may have noticed, Cartesian directions not exactly going to be our friend. So what we can then do is put in our Cartesian operators here, where all of our momentum terms are going to share an HI that comes out front. And then we have x times the first derivative with y, and y times the first derivative in x. Now, it turns out that the central term is also going to be the same thing as the first derivative with respect to phi. So again, phi is the angle around the circle that we're moving. So this actually, by switching from Cartesian directions to cylindrical directions, we actually simplify our system immensely, because now I can get my angular momentum in the z direction simply by taking a first derivative with respect to phi, which is going to become immensely useful. Then this is going to be useful in trying to build up an energy for the rotations about this z-axis. So when I say in the z direction, I'm talking about the rotation about this central z-axis. So my central axis is going to be pointing in the z direction, while all movement happens in the other two. So that's something to keep in mind when we're talking about axes and movement in radial coordinates. So just like our energy can be given as 1/2 mv in radial notations, this is 1/2 inertia times the angular velocity squared, and similarly the angular momentum squared over twice the inertia instead of twice the mass. So these are analogous equations for what we have in one-dimensional movement. We've just replaced mass with inertia and momentum with angular momentum. However, one of the things we have to acknowledge is this just gives us movement in two directions. In reality, we're going to have a molecule that can move in all three dimensions. And I do want to acknowledge this, which means you have to repeat this process for the x direction, the y direction, and the z direction. However, once you add up all three of these individual angular momenta together, this gives us a total angular momenta, which can be used to figure out the total rotational energy of the system. However, we do run into a slight problem. I now have a set of operators. I even now have a decent Hamiltonian to work with. What I'm missing is a wave function. So next time we're going to be tackling the wave function and some of the eigenvalues for two-dimensional motion. In the following lecture, we're then going to scale this up to 3. So next time, let's get in for some real 2D rotation. Until then, take care.